Hi, everyone. So welcome to the N3AS Seminar this week. Today, we have Professor Srimoyee from Iowa State University as our speaker. Sri obtained her PhD in 2015 from the University of Maryland, and then she did two postdocs, first at University of Arizona from 2015 to 2017, and afterwards at INT University of Washington for another 2 years. In September 2019, she moved to Iowa State and joined Department of Physics and Astronomy as an assistant professor. She has a broad variety of research interests, for example, topological physics of matter, chiral transport properties, and quantum phase transitions, etc. In today's seminar, she will tell us about the most recent interesting work on quarkyonic matter in neutron stars. If you have any questions during the talk, please indicate them in the chat window or use the raise hand button. We will have informal discussion later after the talk. So, all right, Sri, please take it away.
Okay, thanks, Sophia, for the invitation and for that very nice introduction. So the work that I'm going to talk about today, I've been involved in this for about 2 years now, or a little more than 2 years. This work, I've been doing this with Ki-Sung, who was at the INT, Larry McLaren, Neil Warrington, both of them, of course, at the INT. Lars Sivertsen is my student at Iowa State. And here, these are the papers that I've written on this topic. So with this, let me get into the topic of my talk. So I'm going to talk about a particular kind of matter that can get realized inside the core of neutron stars. We call it the quarkyonic matter. And I'm going to sort of motivate to you why you should take this kind of description of matter seriously if you were to describe the physics of neutron stars. So here, we are all nuclear theorists, QCD practitioners. So we're interested in the phase diagram of QCD generally. And there are various parts of this phase diagram, some of which are easily accessible, some of which are not easily accessible. So, for example, what I'm showing here is a cartoon of the phase diagram. On the x-axis, I have the chemical potential or the density. And on the y-axis, I have the temperature. And as you know, what this is describing is if you take ordinary matter and either you crush it to extreme densities or heat it to extreme temperature, how does matter reorganize itself under those conditions? Now, at extreme high temperature, we have quark-gluon plasma. That is not something I'm going to talk about in this talk. What I'm going to focus on is the low temperature, high density part of the QCD phase diagram. And as you know, this part of the phase diagram is very difficult to deal with because we don't have analytic calculations that can help us, at least in the regime of intermediate densities. And we also don't have, lattice calculations don't help either because of the sign problem. So it turns out really most of our information about this part of the phase diagram can really come from neutron stars, where moderate density matter gets realized. So a few times the nuclear saturation density is what I'm thinking about. So so of course there are many kinds of questions that you can ask about this phase diagram. The particular one that I am going to focus on today is the square of the speed of sound. So what I want to know is what happens to the square of the speed of sound as you go from very low density to very, very high densities. Now, before I go into further details about that, let me just also remind you the kind of matter that gets realized at relatively high density. And we expect some kind of degenerate nuclear matter or degenerate quark matter to be present at these densities. So degenerate nuclear matter is a Fermi liquid of neutrons or Fermi liquid of neutrons and protons. And degenerate quark matter would be Fermi liquid of quarks. So when it comes to the square of the speed of sound, there are two limits that we already know about. So the very low density limit, we know that the square of the speed of sound would be very small. And then at very, very high density, we again do a perturbative calculation using QCD. And we know that the square of the speed of sound should approach 1/3 from below. So these are the two regimes we have sort of controlled calculation. The question is what happens in the middle? So there are a bunch of possibilities that can take place. So one is that the speed of sound increases monotonically from a very small value, close to 0 to 1/3. And then the other possibilities are, there's a bump, let's say, at some intermediate density. So the square of the speed of sound would violate the conformal bound, which is the 1/3. So it will violate the conformal bound and then come down and then go up again. And you can have multiple bumps as well. Now, one question one might ask is, can we comment on this, or can we say something about this from neutron star observations? Does neutron star observation pick any of these scenarios? And it turns out it actually does. So neutron star data almost rules out, says most likely the case that this does not get realized. And in order to if you wanted to see more of the details, you could look at these papers. So what is most likely to happen is that you're supposed to have a bump. Now, neutron star data, as far as I know, cannot really distinguish between one bump versus multiple bumps. So for now, in this talk, I'm just going to stick with the one bump scenario. And so this is pretty tantalizing. I mean, it's already exciting that neutron star data is telling you something pretty exotic about how the speed of sound behaves at finite density. Now, the question that I started thinking about with Larry and Keithang when I was at the INT is that, is there some kind of model of QCD that can reproduce this kind of bumpy behavior? So it's pretty clear that I cannot really use QCD directly to behave, to predict something like this. But the question is, can I write down another theory that is sufficiently similar to QCD yet can be solved, which shows this kind of a behavior? So so before I go into the detail of what kind of description actually is able to reproduce this behavior, let me tell you what happens if you try to reproduce this behavior with purely nucleonic degrees of freedom. So the square of the speed of sound is, you can write it as the derivative of pressure with respect to energy density. And remember that we are really considering zero temperature here. And then you can write it as the ratio of baryon density divided by baryon chemical potential. And then there's also a factor of the change in baryon density with respect to baryon chemical potential. So this has to be of the order 1 for a few times the nuclear saturation density from neutron star data. So what this implies is that if you consider a change in baryon density, which is about let's say order 1 change in baryon density, that means that you have to have an order 1 change in baryon chemical potential. Now, inside neutron stars, the kinds of densities that we're interested in, the baryon chemical potential is of the order of the mass of the nucleon, a little larger than that. And so the change in baryon chemical potential has to be really large. It has to be of the order of the mass of the nucleon in order for the speed of sound squared to be to violate the conformal bound, which is very hard to get using purely nucleonic degrees of freedom. And so typically what is done is that you put in some repulsive nucleon interactions to get this enhancement in the speed of sound. But this is not very natural. So it would be nice to have a model that doesn't do that. Then we also know that nuclear Hamiltonians are problematic beyond twice nuclear saturation density. This is an example paper to look at if one is interested in that. And then that means that most likely some form of exotic matter is being realized in the core of neutron stars at these densities. So what is most likely to happen is that there is some kind of quark matter which is getting realized. And so we would like to have a description of quark matter which can introduce this kind of bump. But one thing that we want to avoid is a strong first order phase transition as we introduce quarks. So that is the goal of the model that we have in mind, that we want to introduce quarks, but we want to avoid a first order phase transition so as to eliminate the possibility of speed of sound dropping to, again, very, very small values. So so here is one model that can achieve this kind of a behavior. So it's the model of quarkyonic matter, and the idea is the following. So at very low densities, it's the same as purely nucleonic degrees of freedom. It's just neutron matter or symmetric nuclear matter, depending on what you're interested in. And then as you increase the density, then you're supposed to treat the degrees of freedom deep within the Fermi sea as quarks. And you say that the degrees of freedom that are closer to the Fermi surface are nucleons. Okay, so this is the picture, and this was something that was postulated by Larry McLaren and Rob Pisarski in 2007. At the time, they really didn't. They were not really thinking about neutron star data. We didn't even have the data that suggested that the speed of sound really had a bump. They had other reasons to think that matter behaves like this at high density, but it turns out that this kind of description actually fits the behavior of speed of sound from neutron star data. So one reason why Larry and Rob postulated this kind of behavior is that they really had the idea that confinement persists even at high density. So even though you have quark degrees of freedom in most of your Fermi sphere, the degrees of freedom very close to the Fermi surface, you can still think of them as nucleons. So that was really their idea. So now with that, let me tell you how quarkyonic matter can help. So to understand that, first let me tell you how quark matter helps with the rapid increase in the speed of sound. So here what I'm doing is I am comparing the energy densities of two configurations. So I'm going to take a particular amount of baryon density, and first I'm going to store it completely in nucleonic degrees of freedom, and then I'm going to store it in quark degrees of freedom. And I'm going to show you how the energy densities and pressure of these two types of degrees of freedom behave as a function of density. Okay. So on the left-hand side, Nn is baryon density stored in nucleons, and on the right-hand side, Nq is baryon density stored in quarks. Now, Kn is the Fermi momentum of nucleons, and Kq is the Fermi momentum of quarks. And for now, I'm just treating both nucleons and quarks as free particles. Okay. So as you see here, for the quarks, I have an overall factor of NC upstairs. That's just coming from the fact that I have NC types of quarks. And then I'm dividing by NC because I'm counting the number of baryons in quarks. And then this overall factor of 4 is coming from the fact that I am considering symmetric nuclear matter here. So I have 2 flavors and 2 spins. And I'm again considering up and down quarks and 2 spins. So that's why I have this factor of 4. And at this point, I'm not taking into account, the different charges of the quarks and so on. Okay, so I'm just pretending that, I'm ignoring electromagnetism. So now with this, you can see that the nucleon Fermi momentum and quark Fermi momentum, their dependence on the quark density and the nucleon density are identical. So as soon as I set the densities to be equal to the baryon density, Kn and Kq are the same. So their NC dependencies are also the same. Now here, another thing that I'm going to do is to assume constituent quark mass. So the relation between nucleon mass and the constituent quark mass is going to be this. So they are going to be related by a factor of 8. So now with this, let me compute the energy density of the nucleon and the quark configuration. So I'm doing a non-relativistic expansion here. This is just for the sake of simplicity. The first term is the mass density term. So this is the mass energy density. And here I am computing the kinetic energy component of the nucleon energy density. And as you can see, it goes as k to the 5 divided by the nucleon mass. For the quark case, you see that the first term is again the same as what you have for the nucleons. So you have the mass energy density. But then in the kinetic part, you have an enhancement by NC squared. So here I'm not going to take any large NC limits. I'll just set NC to 3. But you can see that this integral, the limits of this integral are the same in both cases because Kn and Kq are the same. Right? The Fermi momentum of the nucleons and the quarks that we found were the same. But there is an overall factor of NC squared. One of this factor of NC comes from the fact that I have NC quarks. And the other NC comes from the fact that I'm writing MQ, the quark mass, in terms of the nucleon mass. So now you can compute the pressure in both cases. So that's given by the baryon chemical potential times the baryon density minus the energy density. And you see that the pressure in the case of quarks is much larger. It's enhanced by a factor of NC squared compared to the nucleons. So having quarks really gives you a stiff equation of state, which can produce a rapid increase in the speed of sound. But we want to do this while not introducing a first order phase transition. So we need to put both of these features together. So, so as I said, that quarkyonic matter is going to be able to achieve this. But what I now want to do is I want to write down another dynamical model from which quarkyonic phase sort of comes out of that model. So again, I can't use QCD to do this, at least not as of now. But is there any other simple dynamical model that will do it? So I want to write down, something like an energy density functional, which you minimize to then look at the kinds of Fermi distribution functions that you're getting. And I want to see this behavior that at low density, I have this all nucleon configuration, and at relatively high density, I have this nested quarkyonic configuration. So this is what I want to do. And so before I tell you what dynamical model that is, I have to first tell you how to label the configuration. Like, how do you identify a quarkyonic configuration, right? So here is how we do it. So first, again, fix a baryon density. And we say that, okay, some of the baryon density is stored in nucleon degrees of freedom, and some of it is stored in quark degrees of freedom. And so now we assume, this is the assumption of quarkyonic matter, that every time there is some amount of quarks in your system, it's going to occupy an inner Fermi sphere inside your bigger Fermi sphere. Okay, so that's the position of the quark Fermi sphere is what we are imposing in the Fermi distribution function. So Kf is the Fermi radius of the quark Fermi sphere, which I was calling Kq earlier. Now I call it Kf. And delta is the shell width of the nucleons. So you know that if you know the radius of the quark Fermi sphere, you can compute the volume of this Fermi sphere and relate it to the quark density, or quark density in baryons. So, or rather baryon density in quarks. So that's what this is computing. And then you can also compute the nucleon density by computing the volume of this outer shell. So everything here you can write in terms of delta and Kf. So both of these densities are computed in terms of delta and Kf. You put those two together, add them up, and equate it to baryon density, total baryon density. And so now what you can do is eliminate delta as a function of Kf, the quark Fermi momentum, and baryon density. And so you just have one parameter, which is Kf, with respect to which you can label your quarkyonic configuration. Okay. So, so now what I want to do is I want to write down a model where the energy density functional behaves the following way. So on the x-axis, I'm plotting quarkyonic configuration. So closer to the origin, I'm plotting some kind of completely nucleonic configuration. And at away from the origin, I'm plotting completely quark configuration. And in between, I have quarkyonic. So what I would like is that at low density, I want the energy density functional to be such that it's the completely nucleonic degrees of freedom or completely nucleonic quark Fermi sphere that minimizes the energy. And at high density, I want the shape of this energy density functional to change. And I want quarkyonic configuration to minimize the energy. So you can imagine, you can think that I'm sort of plotting Kf, which is the Fermi radius for the quarks, on the x-axis. So that might be one way to schematically describe what I want. So here is the model, which is able to produce that kind of behavior for the energy density functional. And it's the simplest thing that I can write down. And that is really the goal. I want to write down something simple. And at this point, I'm not really trying to describe exactly all features of QCD. I'm just trying to write down the simplest thing that I can. So we describe the nucleons using a hardcore potential. So they are like, billiard balls. And so they have a finite size, and I call them V naught. And so as a result, I cannot pack too many of them inside a box. So there is a maximum density for the nucleons, and we call it the hardcore density. So as a result, what happens is that if you try to put N nucleons, big N nucleons, with volume V naught in a total volume of big V, then there is an available volume over which these nucleons run around, and that's given by the total volume minus big N times the volume of individual nucleon, V minus N V naught. And given the situation, you can now define a density called the excluded density, which is related to the exact density. The exact density of the nucleons is the total number of nucleons divided by the volume. So this excluded density is the total number of nucleons divided by the available volume. And as you can see, the excluded density is larger than the exact density. So now, given the excluded density, I can now pretend that I have actually point particles, point nucleons. And I can now use the Fermi distribution function of the nucleons in the shell to relate Kf and delta to this excluded density. So that's the relation between Kf and delta and the nucleon density. And so now I can invert this to write delta as a function of the nucleon density and Kf. Okay, so that's what I do. And you can write down an energy density for this as well. And so this is just, again, I'm taking free particles, free nucleons. So that's the integral that you see here. I'm integrating the energy over the shell. And this overall factor comes from the fact that I have an excluded volume. Okay. So the total energy density is given by this. So what I mean here is that I have both nucleons and quarks appearing as quasi-particles in my picture. So I have an energy density contribution coming from nucleons, an energy density contribution coming from quarks. And this is really, almost free particles. Nucleons are completely free except for the finite volume. They have the finite volume. And the quarks are completely free except for the fact that their constituent quark mass takes into account the physics of confinement. So with this, you can do the minimization, and what you find is that at low density, you indeed get a completely nucleonic Fermi sphere. So you find that Kf is 0. And at relatively higher density, you see that Kf is not equal to 0. So you start making quark matter or quarkionic matter. Now, I'm not going to show you an explicit derivation of the minimization, but I can sort of intuitively tell you by some estimates as to why this is happening. So in order to understand this, we can compare the energy densities of an all nucleon and an all quark configuration. So let's first look at an all nucleon configuration. So we set Kf to 0. So the inner radius is 0. So in that case, as you can see from here, Kf is 0. You can relate delta to this excluded density. So that's what I've done here, right? Delta cubed is related to the excluded density. And now I can compute the kinetic energy density of all nucleon configuration. So I'm dropping the mass energy density because it's the same in nucleons and in quarks. So if you look at the kinetic energy density that I had written earlier, so it goes as k to the 5, right? So if I integrate from 0 to delta, delta is the top of the Fermi surface for the nucleons, it goes as delta to the 5 divided by the nucleon mass, right? And note that because I was in an excluded volume case, I also had a factor of 1 minus nn over n naught. So if I put that factor here, I get delta to the 5 times 1 minus n nucleon over hard core density. And there is a 1 over nucleon mass factor, which I'm ignoring because it's also going to appear in the quark case, okay? So it goes as this, and I plug in the expression for delta in terms of the hard core density. And you see that I have a singularity here, which again goes as 1 minus n nucleon over the hard core density. Now I can do the same exercise for quarks. So in that case, I set delta to 0, and I have everything, all the density of nucleons is stored in the quark Fermi sphere. So I evaluate this. So I get an N3 square, and I get a Kf to the 5, where Kf is the quark Fermi momentum. And so that's what I get here. Now note that Kf cubed is equal to the baryon density. So Kf to the 5, I can write as Nb, baryon density to the 5/3. And the same thing has come, the same baryon density to the 5/3 factor is coming here. It's just coming from this delta to the 5. So now what you can see here is that if baryon density is too small, then storing baryons in quarks is Nc square more expensive than storing baryons in nucleon form. So all the baryons like to be in the nucleon form. And then at some point, this singularity starts dominating, and the energy cost of storing nucleons becomes comparable to the energy cost of storing quarks. And at that point, you start making quarkionic matter. So that is really the intuitive explanation for what we are seeing through the energy minimization procedure. So we have been able to achieve what we what the goal was. And so now I'm plotting the square of the speed of sound as a function of the baryon density written in terms of the saturation density for some values of the parameter. And you see that I am indeed able to achieve this bump. And the hard core density has been set at like few times the saturation density, 3 times the saturation density in this case. So this was sort of where I would like to end. But since then, I have done some more work. So what I've described to you was symmetric quarkionic matter. So I had symmetric nuclear matter, symmetric quark matter. But then I wrote a paper with my student where I extended this model to neutron matter. And then you can try to see to what extent you can fit neutron star mass radius data. And here is one set of parameters for which you describe neutron star data pretty well. And then I wrote a paper with Neil Warrington on finite temperature description of symmetric quarkionic matter. And so that's this paper if you're interested in that. And I'm happy to discuss both of these papers. If you have questions, I just didn't want to include them in the talk itself. So with that, now let me end here. So there have been quite a few follow-up work. Diana, who is I think in the talk, Jiong and Hernandez wrote a paper on including strange quarks in this description. Beta equilibrium was considered by Zhao and Latimer. They didn't have the excluded volume model. They were looking at a different model. And then the stuff to do next is, for example, finite temperature analysis of quarkyonic neutron matter. So quarkyonic neutron matter is something that I already wrote down with my student for the excluded volume model. And then beta equilibrium at finite temperature, transport properties of quarkyonic matter. So these are some of the questions that I'm thinking about right now. So with that, I'd like to thank you. And if you have questions, I'm happy to answer.
Thank you, Sri, for this interesting presentation about quarkyonic model in general. And so are there questions? Please raise your hand. Yes, I see. Josh, please go ahead.
Thank you, Shi. That was very, very, very nice talk. I very much enjoyed that. And finally learned something about trying to understand quarkyonic matter. So this is very, very nice. So I was going to ask about extending this to finite temperature. It seems like, your kind of very zero temperature, your heuristic kind of derivation, it still goes over. I mean, as long as the temperature is fairly modest, but now you have, high energy tails on above the Fermi surface,
yeah,
right, above the chemical potential for the quarks and so that's just introducing more, a smaller number of higher energy particles. And I'm wondering what that does. Does that just affect the speed of sound curve that you showed, for example, or is there something fundamental on the balance here that changes as well?
So, I mean, I was working on this with Neil for like last year. I was working on this with Neil Warrington. And what we concluded at the time was that this is what happens to the Fermi distribution function. So the inner quark Fermi sphere doesn't get affected. The degrees of freedom, which are close to the Fermi surface, which are the nucleons, those get affected. And the particular question that I was interested in that case was what happens to the quark onset density at finite temperature. We really didn't look at what happens to the square of the speed of sound. This is something we plan to do, but we haven't yet done it. But in order to understand, like, what happens to the energy minimization, so this is the first thing to take into account, that your nucleon Fermi sphere will get this tail, and on top of that, in this case, when you have finite temperature, you'll have to minimize the Helmholtz free energy. So I will also have to give out entropy functional, which we wrote down. It's again, we assume free particle, except for the fact that I have this confinement physics coming through the constituent mass and this hardcore interaction. So that's the status of what we have done up till now. Yeah. And we haven't looked at the square of the speed of sound at finite temperature. I'd like to look at that.
Very good. Thank you.
Yeah.
We have a week next.
Sure, again, it was a really nice talk. I always have a little trouble wrapping my head around pictures of Fermi spheres like that, but I have this naive view that in systems like the dense systems of this sort, that what's important about the surface of this Fermi sphere is that that's where all the transport occurs. So I'm trying to understand what this means in terms of this model. Well, what does that mean? That only the nucleons participate? Because you've got these quarks buried deep in this Fermi core, so they can't do anything but just exist.
Yeah, it seems that that's what the suggestion is. So it's like the quarks contribute significantly to the equation of state.
Yeah.
But when it comes to the transport, it's the nucleons which will contribute to the transport.
It's really interesting and really weird.
And there is one similar concept which you have, I'm sure you have come across this, which is the idea of Cooper pairing.
Yep.
So you have this bound state of fermions at the Fermi surface because of the instability, and so it's kind of similar to that, except that for Cooper pairs, the size of Cooper pairs are really large, right? These are Cooper pairs are bound states that are really large in size, but these are like nucleons, so the sizes are not as large. So that's one difference.
Very nice. Thank you.
I think transport must be affected by all constituents. I don't see how one constituent can stay mute.
Sorry?
I don't see how one constituent in the star can stay mute in transport.
Well,
if the-
yeah, go ahead, Vic.
Yeah, I was just getting, if the Fermi surfaces look like what was shown, then that would be the consequence of that, just because you can't, there's no inelastic scattering anywhere but at the surface.
Yeah.
So I understand how this happens physically. Transferring it to the picture of the of the neutron star as a function of distance is kind of hard for me, but
Well,
that's what this Fermi
thing is,
sphere picture suggests.
well, the thing is a little below and a little above the Fermi surface,
Here.
but both of them have to contribute. I don't see how one can stay mute.
You will not be able to access this. So if you take the distribution function that I'm writing down and just compute the, take some observable that you're interested in and try to compute the, weight it with the distribution function and compute it, the most of the contribution is going to come from here.
Not at finite temperature.
Yeah, finite temperature, this is where the tail is. The tail doesn't reach here. So that's what it looks like. So your quarks are like, deep within the Fermi sea. So that's really what the expectation is.
I find it hard to believe.
I think Tianqi, you are the next.
Okay, following the previous question, so all the transportation property is not affected by this model, basically, because we are
unless you are at really high density, at which point your finite temperature will access the quarks. I mean, this is really not that different from what happens even in quark matter. If you have a large gap, right? So you will not be able to access the deep, what is happening deep within the Fermi sphere, even in that case.
Yeah.
So it's not that unusual.
Okay. Yeah, I know your model replace the shear thickness formula by the excluded volume thing, so that you do not need the shear thickness formula anymore. But still, both model will require the layout of the Fermi sphere, right? How the nucleon shear is on top of quarks. So that thing. So there be a few different ways to lay this layer. So do you have more insights on the choice we are making here?
What do you mean? So you don't want to have a sharp change between where quarks are and where nucleons are. You want to have
so what's the relationship between the lowest quark nucleon Fermi momentum and also the quark Fermi momentum? What's the relationship between them?
So they are both defined by the same Fermi momentum, which is the top of the quark Fermi sphere, right? So this KF is what decides where nucleons end and where quarks end. Now you could try to imagine a case where this is sort of fuzzy, so nucleons extend somewhat beyond KF and quarks extend somewhat beyond KF as well. But yeah, you could do that, but I don't think that that's going to be affecting any of the main results of this, if unless quarks, most of your or rather unless your shell width delta is small. Okay, so I don't think the equation of state is going to get affected by a lot.
Yeah, just some
the
details.
Transport properties might get if you are, for example, if you are high density, if you're at high density, right? So that your shell width is really small and the temperature can access the quarks. At that point, it will really matter, what you're doing with how you're overlaying the nucleons and the quarks.
So if you do not consider like up-down quark or a nucleon and protons, then you are considering the like Fermi momentum directly. But if you have up and down and proton and neutrons, this thing is not that obvious. So that's the reason I worked with Professor Latimer on this project about how to add the beta equilibrium into consideration, things like that.
Yeah, so for that, I mean, I didn't include explicit beta equilibrium in a paper that I wrote with my student. What we had there, we just had pure neutron matter in the nucleon sector, and for the quark sector, you just impose charge neutrality, and that tells you what is the amount of up and down quarks. Okay. And so for the corresponding excluded volume model, you could take a look at that paper.
Okay. Okay, thank you. That's a very nice talk.
Thanks.
Let's move on to the next question from Pedro. Yes.
Hi, Sri. Thanks for the nice talk. I was curious about observational constraints. So can you please show those neutron star mass radius relations?
Oh, yes, yeah. Hang on.
Okay, so is the main effect here a softening of the equation of state at high densities so that you get like lower mass high, lower mass for the maximum?
It's stiffening is what
you get. Interesting. Okay.
And now these are actually pretty high. So these are for one set of parameters. You wouldn't really want that high neutron mass, neutron star mass, but there are ways to adjust the hardcore density, for example, so as to bring this further down, closer to 2.2 or something solar masses.
Okay.
Yeah.
And is there any physical reason to not have a high density deconfinement phase transition, so pure quark matter after this phase transition?
So this is not a phase transition, right? Okay. We are deliberately trying to avoid phase transitions here. So that's why we have the nested Fermi sphere. Because if you have a first order phase transition, what happens is that there's a region of space. Part of it is occupied by one kind of phase, and parts of it is occupied by some other kinds of phase. And so in that region, as you're going from one phase to the other, these bubbles form, and that makes the pressure stay flat and drops the speed of sound. And this is not what we want to do. So that's why we introduce quarks in the momentum space and not in position space.
Okay.
So that's why there is no phase transition. But yeah, you can have a phase transition beyond the kinds of densities that I am looking at here. Yeah, so but I'm guessing that you would not want them to again drop your speed of sound so low that you have low neutron star masses and so on.
Thank you.
Okay, so Mia, I think it is your turn.
Actually, I think it got addressed by Wick's question. I just need to think about it more now.
Okay, good. So actually staying on this plot for mass radius, I think in this paper, you also mentioned how the previous problem about quark contents extended to too low density, which contradicts with the nuclear matter calculations. Can you elaborate a bit on how this was addressed here when you calculate?
So there are, I mean, for this I have to give you a background. Typically when quarkyonic matter comes in, quarks come in, there are some non-analytic behavior in the equation of state which you don't want, because that is precisely what quarkyonic matter does not want to incorporate. It doesn't want phase transition like that, or it wouldn't even be a phase transition. It would be inconsistent because I'm doing everything in momentum space, right? So that's the first point. So for that, in the paper with Larry and Kisang, what we did was to introduce a regulator which would introduce quarks smoothly. So the quarks get introduced, but they have a smooth enough behavior that you don't get something nonsensical happening when they are coming into the picture. So that was what we did. But then what you see is that if you introduce the regulator exactly the way we did, what happens is that even at somewhat lower densities, you have some radius of quarks appearing. So it's the nucleonic Fermi sphere that we wanted is actually has a small radius of quarkyonic Fermi sphere inside it, which we don't want. The size of it is small, but it's still there, and we didn't want it. So what you do is you have to change the regulator. You have to change the regulator smoothly, so it has to be very, very small at low densities. And then the regulator sort of also picks up at the same time when quarks come in. So at around sometimes around a few times the nuclear saturation density. So that way, you get the physics of this excluded volume to kick in around hardcore density, but you also don't introduce quarks at low density. So that is how you would address it.
Yeah, so for example, still you have some characteristic density that quark contents become significant, right? For the equation state.
Oh, yeah. Yes. Yeah.
And do you know like roughly at what mass for neutron stars that density is on this plot? It's pretty small, right?
Yeah, so in this plot, it would be difficult for me to remember. I don't remember right now, but I believe what we had was we were setting the hardcore density to be 4 times the saturation density. So around 3 times, 3.5 times saturation density is where we were seeing quarks appear. So yeah.
Yeah, that's roughly 1.4 solar mass.
Right,
Usually it's 3 times saturation density. Yeah. And for low density part, I think you have applied the quantum Monte Carlo calculation, the phenomenon potential, right?
Right,
which is pretty soft. Yeah.
Yes. So for the so this is the potential we used for the low density part. This is something I just picked out from Sanjay's paper with Larry.
Yes.
So that's, I mean, we're planning to improve this, but this does pretty good job. So this is what we used.
Yeah, great. Yeah, thank you so much. Yep. Are there any additional comments, questions from the audience? Okay, I do not see more hands up for comments in the chat. Let's thank Sri again, and thank you for coming. See you next time.
Thank you.
Bye.
Yep. Bye.
Thank you.
Thanks, Sri.
Thank you.
Thank you.